Hi everyone, you are welcome to Eagles Concept Learning Room. In today's session, we pick up from where we left. We've been looking at the general wealth properties when it comes to the senior secondary physics. So after doing the general wealth properties, I'm sure there are two major examples that we are able to pick from. We said one of the examples of the two major classes of the wave was sound, which was an example of a longitudinal wave, and light as an example of a transverse wave. So in today's lesson, we're going to pick it up with looking at sound as a longitudinal wave. We want to understand what sound is. We look at it in details. Don't forget to subscribe to our channel and to like our Facebook page at Eagles Concept Academy. For any queries, you can contact us on our WhatsApp line 4976 64 75 31. All right, let's go straight into today's lesson. What is sound? So in simple terms, we are saying sound can be defined as a wave of energy or vibration into our ears from various objects. Sound is simply defined as the form of energy that can be detected by our ears. That is what we can say in simpler terms. So sound is caused by a vibrating object. So whatever object has the ability to vibrate, it can simply produce what is called sound. So for example, the flickering of a ruler, when it is flicking, it can produce sound. The vibration of some doorbell, that produces sound as well. All right. Sound is created when something vibrates and sends waves of energy into our ears. Exactly what we are from explaining. So we are saying the vibration travels through the air or other media. So in short, we are saying for sound to move from one place to another, it has to travel through a medium. So sound cannot travel through a vacuum. It needs a media to travel through. For example, the mediums that we need, it can be a solid, it can be a liquid, or it can be in a gas. So these three states of matter, sound can travel through. However, it is important to note that in the three states of matter, sound will travel through at different speeds. All right, so having mentioned that, you also know by now to say the speed of sound in air is actually about 340 meters per second. However, that value is dependent on other factors such as temperature. Now, we'll look into details so that we can understand that statement later on. But for now, all we are trying to say is sound, it needs a medium, which can be either a solid, a liquid, or a gas. Now, before we can continue, let me just say something. Now, sound will travel fastest in a solid because the particles in a solid are closely packed together. So, because the particles are closely packed together, the energy can easily be transmitted from one particle to another, then followed by a liquid. In a liquid also, they are not closely packed, but they are at least not further apart. So also there it can be easier to transfer. But in a gas, the particles in a gas, the gas molecules actually are further away apart. Therefore, it becomes slower to transfer sound in a gaseous state. So listed in order of how fast sound can travel in these states of matter, we are saying solid is the fastest, followed by liquid, then the least is the gaseous state. And the explanation to this is dependent on the way the particles are arranged in these various states of matter. All right. The stronger the vibration, the louder the sound. So sounds are fainter and the further as you get from the sound source. All right. Let's look at some of the properties of waves that we need to understand if we are to successfully complete this course about sound. So we are saying sound waves, they travel at 340 meters per second in air. So this is the speed of sound in air. Like I said, air is just a mixture of gases, so this is the least. But when you put it in water, you expect it actually to move a little bit faster. For example, most of the common values you find is 1300. Okay, so you're going to, this is 340, so you're going to find 1300. So that is the speed. It is a little bit faster it is a little bit faster in what? In water. Then it is fastest in solids. So that is just the general rule. And also, this value in air also, it varies from time to time depending on the temperature, or rather the weather conditions of the day. Now, when the temperatures are high, it means the speed of sound becomes slow. Okay, the speed of sound reduces. When the temperatures are high, the speed of sound reduces. Now, think of it as this way: when the temperatures are high, it means that the particles of matter are actually further apart. When the temperatures are high, the particles of matter are further apart. Therefore, the rate at which the energy is being transferred will be slow. But when the temperatures are lower, it means the particles are closer together. So if the particles are closer together, it means that the rate at which the energy is being transferred can be very fast because the particles are closer together. So hence the reason why we are saying the speed of sound in air is also influenced by what? Temperature, because high temperatures will cause the particles to be further apart, which is almost like that one of a gas. So therefore, the speed will even be what? Will even be slow. Okay. So I'm sure this one is making sense. This one is making sense for people. So the speed of sound in air is actually about 340, but compared to light, the speed of light is actually very fast. This is how come during the rain season, the first thing that you observe is you're going to see a flash of light before you can hear the thunder. So the flash of light is seen first because light is fastest. It travels fastest compared to sound. All right. The second property is that sound travels as a longitudinal wave, which means that the compressions and the rarefactions of sound waves result in small differences in what? In air pressure. Now, we looked at these things when we are looking at the general wave properties. So we know that longitudinal waves are waves in which the vibration of particles is actually parallel to the direction of travel of the wave. Okay. Sound wave travels faster. Just to re-echo the point that I've explained, we are saying sound waves travel faster through liquids than through air. So sound travels fastest through solids. This is because particles are linked most strongly in solids. However, sound must have a medium through which it can travel. Unlike the electromagnetic waves, sound will not travel in a vacuum. So just trying to re-echo what has been explained already. So that has been the properties of sound. As we are talking about sound, it is also important that we discuss pitch. Okay, now what is pitch? With reference to sound, we are saying pitch is simply the quality of a sound. Okay, the quality of a sound. Is it high? Is it low? And usually this depends on the speed of what? Vibration. So the more, the faster the vibration, the higher the pitch of sound. The lower the vibrations, the lower the quality of sound. Okay, so different materials produce different pitches. If an object vibrates quickly, we hear a high-pitched sound. And if an object vibrates slowly, we hear a low-pitched sound. So high-pitched sounds have a high frequency. So please take note, in the exam, you'll be required to understand the relationship between pitch and frequency. So there is a relationship between pitch and frequency. So the higher the frequency, the higher the pitch. The higher the frequency, the higher the pitch. So examples of high pitched sounds include bird songs, and even the voices of girls or ladies or females per se, they also have a higher pitch compared to the what? They have a higher pitch compared to the sound of the males. The males, they have a bass in them, but the females, they have a higher pitch. Okay, so uh, low pitch sounds have low frequency. So the higher the frequency, the higher the pitch. So the pitch of sound is influenced by what? Frequency. And like I'm saying, it's simple. The lower the frequency, the lower the pitch. The higher the frequency, the higher the pitch. So examples of low pitch sounds includes the horn of a ship and the bass guitar. Now, the bass guitar will produce that bass, but the lead has got a higher pitch. The lead guitar has got a higher pitch because it's going to produce that sound which is like, but for the bass it will be do 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 do. So that's the difference. So a higher pitch, like I said, also the voice of a girl and the voice of a boy. At least the voice of a boy will have a bass, be like hello, hello. But the voice of a girl will be very high pitch. Hello, how are you? So those are some of the differences that we are able to talk about. All right, we are still talking about the properties of sound. So the human ear can detect sound with pitches ranging from a frequency of 20 Hz to 20,000 what? Hz. So this range here from 20 Hz to 20,000 Hz is known as an audible range of frequency. So audible range of frequency. Now, this is the only frequency which can be detected by the human ear. So what we are saying here is very simple. If the frequency of a certain sound being produced is lower than 20 Hz, then we can't hear it. This is probably one of the reasons why we can't hear the ants. The ants, they talk, probably they sing, they even talk behind our backs as we step on them. But because they've got a lower frequency, we can't hear them. Okay, we can't hear them. Then 20 Hz, but anything between anything like 21 Hz, anything 100 Hz up to 20,000 Hz, this one we can hear it as humans. Okay, now if you go above, now this one is called an audible range of frequency, and it is the safest because any frequencies above 20,000 Hz, when you convert from Hz to kilohertz, this one will be 20 kilohertz. Okay, so this one will just be 20 kilohertz. All right, so now anything above this will actually be so damaging to your ears. It can damage your ears. This is how come, if you notice, if you're using a good phone like a Samsung, when you're increasing volume, they will even warn you to say this sound is too high. If you exceed, you might damage your ears. Now, the damaging of the ears does not happen there and then. It happens slowly until someone becomes has some serious defects. All right, so sounds with frequencies above this range. So this one we have called it an audible range of frequency. So this one here we are calling it an audible what? An audible range of frequency. So this one here all the way up to there, we are calling this one an audible range of frequency. But any frequencies that are above this one, we are calling it ultra what? Ultrasound. Now, ultrasound is used by animals, carnivores like bats for navigation, okay, and by doctors for looking at unborn. You've heard of a woman is going for ultrasound. They want to check the sex of the baby. They want to see the position of the baby. So they'll use ultrasound. So ultrasound is simply any sound that exceeds a frequency of 20 Hz, 20,000 Hz rather. All right, so in conclusion here, we are trying to say the greater the frequency, the higher the pitch. So pitch and frequency, they are related. Please take note of that. Pitch and frequency, they are related. Let's talk about loudness of sound. There's also loudness of sound. You've got volume. When you put the volume there, you can see that the sound has become louder. When you reduce the volume, the sound has become less loud. Now, what is loudness? So we are saying loudness simply refers to how loud or soft a sound seems to a listener. Okay, so the loudness of sound is determined in turn by the intensity of the amount of energy in sound waves. So the unit of intensity is the decibel, dB. So sound is measured in decibel, which is dB. So with reference to sound, now we are saying with reference to sound because decibels are also used in other things, okay? Are also used as units in other things. But when it comes to sound, we can define it as the quietest sound that can be heard. The quietest sound that can be heard. That is what we call a decibel. So a decibel is a quietest sound that can be heard. All right, so in conclusion here, we're saying the greater the amplitude, the louder the sound. So now get these two. Pitch is related to frequency. So the higher the frequency, the higher the pitch. Now loudness is related to amplitude. So the greater the amplitude, the louder the sound. The greater the amplitude, the louder the sound. And in case we forget, we are saying sound is simply caused by the vibrating of objects. So anything that can vibrate can produce sound. It can be a flicking fork, a flicking knife, a flicking ruler. It can be a spring. Even when you throw a spring down, you can hear it make some sound. When you just bang on a certain thing, because there is that vibration which is there, then sound will be produced. Get that into your head. In case you meet diagrams in your exam, you know as long as it's about vibration, then you know that sound is involved. All right, now we are talking about sound, and we've said the speed of sound in air is actually about 340 meters per second at RTP, because when the temperature conditions changes, the weather conditions changes, we are likely to have some values which may vary from 340. Okay, and we have explained the reasons for that. It's because of the arrangement of particles at that time of the day. Now, when determining the speed of sound, we can use two methods. So the speed of sound in air can be determined by two methods. So the first method is called pistol method. Other people can call it gun method. Other people can call it flash method. Whatever name you call it, the principle is basically the same. So number one, I'm calling it the pistol method or the gun method. Now, sound travels much more slowly than light in air. Light has got a speed of about 3 multiplied by 10 to the power 8 meters per second. So we are saying it has got, so light has got about 3 multiplied by what? That is about 3 times 10 to the power 8 meters per second. Now compared to sound, which is just about 340 meters per second. So you can see the difference. This one is much faster. This one is very slow. It's almost 10 times faster. So light is almost, I think it's beyond 10 times 10. This one, no, it's actually 1,000 times faster. So it's very fast. So light is very fast compared to what? Just compare these two values. How many times does because let me just punch on my calculator so that we have the correct estimation here. You can punch on the calculator. So we enter the 3 with 8 zeros. So 8 zeros, 8 zeros. So that is 300 million. You divide that one by 340. Wow, wow, thousands and thousands faster, because this is like 882,352.94 times faster. Okay, so it's really fast. So this method is based on the fact that light travels faster than what? Sound. The second method is what we call the echo method. Now, echo is simply the reflection of sound as it hits smooth or hard what? Object, and this causes what we call a repetition of what? Sound. So that is what an echo is. So the echo method is based on the ability of the sound to bounce back or reflect when it hits a smooth surface or any hard surface. Let's look at these experiments in details. This is how you can set up. When you're setting up an experiment to determine the speed of sound in air using the pistol method, you can actually set up as shown in the diagram here. So you need two people. So person A is the one who's going to have a gun. Then stand at a distance and make sure you are at an open ground. So stand at a distance so you can measure this distance between person A and person B. Measure it as D. So you measure the distance D. So person A is going to have a pistol, person B is going to have a stopwatch. So what is going to happen here is very simple. Person B is going to be observing person A. So as person A fires, person A will be looking into the air. So this person A is firing, not pointing the gun at person B, but pointing the gun in the air. So as person A is pointing the gun in the air, person B will be observing, and the fingers touching on the start and stop of the stopwatch. Okay, so that upon firing, this person B, the first thing person B is going to see is the flash, because remember, light travels faster than sound. So the first thing person B is going to see is the flash. So the moment person B sees the flash, they are going to start the watch. Then the moment they hear the sound, they are going to stop the watch. The watch. Then they have recorded what we are calling time. So time will be recorded in what? Seconds. And remember, when they were beginning the experiment, they also stood at a distance between A and person B. This is the distance D. Then to determine the speed of sound in air, we are going to use the ordinary formula, which says speed is actually given by the formula distance over time. Remember, this one, the distance here has got is measured, the SI units for distance is meters, and the SI units for time is what? Seconds. Therefore, the SI units for speed will be given by meters per what? Per second. So always be sure that it is in meters per second. Remember, this is the general and standard formula that we know, but there are other formulas because speed is a wave, okay, it also obeys the general wave equation, which says speed given by V is equals to actually wavelength lambda multiplied by what? Frequency. So even this formula can also be valid. Now, with respect to this particular experiment here in the picture, this is the formula to use. Let's look at one example, see if we can calculate. Okay, so a musical instrument produces a sound wave with a frequency of 100 Hz. So data collection is very important. Let's collect the data. So we collect the data, and we are saying a musical instrument produces a sound wave with a frequency of 100 Hz. Okay, so frequency F is given us as what? 100 watt, 1000 Hz, so 1000 Hz. Then the sound wave has a wavelength, so they've been given us wavelength, which is given by lambda. So wavelength lambda there is actually equal to 0.34 meters. Now, assuming this wavelength was given in centimeters, we are supposed to convert to meters. You know the drill by now. Calculate the speed of sound. So speed of sound, it can either be S or V. So V or S, it's one and the same thing, which is question mark. So from the data that we have here, we know that this formula speed is equals to distance over time is not going to work. Why? Because we don't have time. So because we have frequency and wavelength, the best formula to use is speed is equal to lambda multiplied by what? Frequency, like that. So this one will easily be equal to 1000. So 1000 Hz multiplied by 0.34 meters. So 0.34 meters. Then you can punch that one on the calculator, and you're going to find your value of 340 meters per second. So don't forget the SI units, they are very important. So 340 meters per second. So you've seen the first method of determining the speed of sound in what? In air. All right. Let's look at the echo method. As already defined, echo is simply the bouncing back of sound as it hits a smooth or hard wall. Then this causes a repetition of what? Sound. Now, how do you carry out this experiment? So it's very simple. You are supposed to set up. Now, in the exam, they also ask you to describe this thing. So please, you can play, pause, write your own notes out of what I'm explaining here. So we are saying you set up as shown here. Now, you still have person A and B. Now, this person A and B, they are not standing on opposite sides, or it's not like this person A is in front and person B at the back. No, these are actually on the same line. They are standing on the same line. It is just a drawing here, so please take note. They are standing on the same line. So they stand on the same line and they stand in front of a wall. So they stand in front of a wall. Why? Because this wall is going to reflect the sound. So the distance the distance from this guy here, person A, person B to the wall, and person A to the wall is just the same. Okay, it's just the same. So now we'll focus on person A. This person B is just having a stopwatch. So this guy here, person B, is having a stopwatch. Then this one is having anything that can be used to produce sound. Sometimes you can even clap your own hands. Sometimes you can use pieces of wood to bang them together. So what is going to happen here is person A is going to bang or hit these planks together. As she does that, because of the vibrations, sound is going to be produced. So as the sound is being produced, it is going to hit on this smooth and hard wall, then the sound is going to bounce back. So the sound will move like that now. Sound will go, it reaches the wall, and then it bounces back again and comes back. So this guy here will be listening. So this guy here is going to listen to the sound. So the moment the person A, the girl, bangs the planks together, the person with person B will start the stopwatch. Then they wait for the sounds. Now remember, echo, you will find that when you speak, I'm sure you've encountered this, when you speak, you'll be like, ah. When you wait a bit, when you're in an open space, you hear another person trying to imitate you. Again, you hear, ah. So this is exactly what is going to happen here. So this person A is going to bang these things like, bah! And then as soon as they hear "po," person B will start the stopwatch. And then as soon as they hear another person repeating or imitating person A, again by "po," after some time, then the stopwatch they'll stop it. Are we together? Then the stopwatch will record the time. So whatever time is showing on the stopwatch, that is the time. Now, whenever you are using the echo method, you are going to use the formula speed is equal to 2D over T. So whenever you're using the echo method, so whenever echo is mentioned, this is the formula to use. Now, why? Remember, when this girl claps here, this distance here is D, we measure it. And then again, when sound bounces back, it will come back the same distance again, which is D. So you have this D plus this D gives you 2D. So whenever an echo is mentioned, or you figure out the statement is implying an echo, then the formula to use is this one. But if no echo is mentioned, then the formula to use is the normal formula. S is equal to D over T. Are we together? So note the difference. This one is an ordinary formula. Use it when no echo is involved. But whenever echo is mentioned somewhere, they might not necessarily say echo. They can say sound bounced back. Then you know that, okay, the bouncing back of sound is an echo. So the formula to use is this one. And the reason is because sound travels twice the same distance. All right, so that is how you describe, and that is how the experiment can be done. Let's look at the sample calculation. A man claps his hands on a hilltop. He hears the echo 0.7 seconds later. If the speed of sound is 340 meters per second, how far? So how far? Already they are asking for distance. So the first thing that we do here is data collection. So we collect our data. So as we are collecting our data, they are saying he hears the echo 0.7 seconds. Now 0.7 seconds, that is time. So just from the SI units, we can tell that time was actually 0.7 seconds. So time 0.7 seconds. Then they've given us that if the speed is actually equal to 340 meters per second, so this is 340 meters per second, how far? So we are looking for the D here. Okay, D is question mark. Now, because they've said a man claps his hand on, he hears the echo. So echo has been mentioned, meaning the formula to use is speed is equals to 2D then over T. So because we are looking for D, we can make D the subject of the formula. We just cross multiply here. We are going to have our 2D is actually equal to st. Okay, so s times t, that is st, then 1 times 2d is 2d. So we divide by 2, also by 2. So that one goes, so we have d is equal to st. So this is st over 2. So we can substitute into that one. The s, we know that that one is 340 meters per second. So 340 meters per second multiplied by 0.7. So this is 0.7 seconds over 2. You can easily punch that one on the calculator, and you're going to find a value of 119 meters. So this is our distance. All right. Number 2. Now this experiment is actually very useful. So this example that you're looking at, example 2, is practical actually. This is how they even determine. They will tell you the Indian Ocean is so meters deep. Who went there to check? Now, they don't actually go there. What they use is very simple. They just use these same experiments like this one that has been shown here. So this is exactly how they determine the depth of a river, the depth of a sea. It's not like they literally go there or they use the long rulers. No. They don't. They use the same method here. So please, this is very practical science. We apply it in our everyday life. So this topic that we are talking about, sound, sound and the concept of the echo, is used in determining also the depth of rivers and other sea bodies. Okay, so the diagram shows a ship using an echolocator. So we've heard of sonar. There's been a movie called Sonar, to find a shoe of a fish. The pulse wave is transmitted from the ship, which is then reflected off the top of the shore and is then picked by the. Now, the shore here, this fish here is going to reflect back the sound. So the ship is going to send the sound, okay? So the sound goes, when it hits the shore of this fish here, it bounces off, it goes back. So here, you see, this one is a detector here. So this is the one that is detecting. So this one is a transmitter, it sends the sound. Then when the sound comes back, it will be detected by this one. So the only thing that you need is to have a stopwatch. So the moment the transmitter sends, you start the watch. Then when the detector also detects the sound, so actually you don't need to do it manually because these things are automated. So they've also fixed a stopwatch here. So a stopwatch will start the timer the moment the transmitter sends the sound, and then it will also stop automatically. So these things are automated. So that is how it is done. Okay, let's continue with our question. So they're saying, given that the speed of sound in water is about 1300 meters per second, and that the time taken to receive the echo was what? Was 2 seconds. So already there is echo mentioned here. So the formula to use, but before we rush to the formula, let's just deliberately and normally collect the data. They've given us the speed, which is actually 1300 meters per second. Then they've also given us the time because they've said the echo was 0.2 seconds, so 0.2 seconds. So this is the time that will be given. Then we are looking for now, calculate how deep. So how deep the ship has to lower its fishing net. So that is distance. So distance is equal to question mark. So just like the other question, we are going to write that speed is equals to 2d. Why 2d? Because we know that there is an echo involved. So over t, we can make d a subject to a formula like we did. We're going to say 1 times 2d, this one will be 2d is equals to st, s times t, that is st. Then we divide by d. Also, we divide by 2 rather. Also, this side we divide by 2. So that this and that goes. Then d is equal to st. So this is st over 2. So substituting into this one, we know that we're going to have 1300 meters per second as our speed, multiplied by 0.2 seconds, then divided by 2. Punch that on the calculator, you're going to have a value of 130. So this is 130 meters deep. And you have found the question. All right, so this is about sound. Let's practice. For my students, uh, you can you are expecting actually to have an exercise after this, so that we see whether you've been understanding or not. But for my YouTube videos, the best you can do for us is like our YouTube videos, like our Facebook page, and share, inform others. You might be helped in one way or the other. A lot of people have sent messages, seen how it has helped them in one way or the other. But if you are interested, you can contact us so that we can see how best we can help each other. But for now, this is where we end with today's lesson. So thank you so much. Till next time.